Okay, so this is going to be the first step in the assembly of our power astronomy dynamic sensor, our pads. And what I've got here is just a standard Uno. This is an Arduino Uno. And we buy these in pairs for about $15 for the pair. So you're looking at, $7, $8 for each one. And then this is nothing more than a mount effectively for the breadboard here so that it could go on top. You don't strictly need this. You could actually have it, sitting off to the side or something, but it's pretty convenient because then if you decide that you need a motor driver and you don't need all of the electronics on here, then you can simply remove this and replace it with a motor driver board. So the only thing to be careful about when you're putting these together is making sure that your pins line up. You'll notice that not all of the pins not all of the holes on the Arduino are going to match up with the pins on the board here. Those are the extra power pins and things like that. What I will often find is that these pins will actually get bent, and so they'll be outside of it, and that's a quick way to fry your board. Now you could leave it like this and just have it exposed, and actually doing it this way will keep this mounted in here fairly well. It'll be nice and tight, and you're not going to have a problem with this coming out. And if this does come out, well, that's when you end up smoking these things because you get the power crossed on it. However, they're students. They're probably going to drop them a few times. So we've found that these cases, these molded cases, do a good job. Now you can also, I got these on Amazon. They were fairly cheap, about $5-6 each. You can find a laser cut acrylic version that assembles. Avoid those. First of all, they make the board too big to fit on the carrier that we're about to put on here. But second of all, they're very brittle, and so they break extremely easily, and so they really don't do the job for what you need it to do. These are also very, very easy. It just slides right in there. Take the top part, and it just snaps on like so. And now you've got an easy way to connect this to your base. And we've done that here on this one. And I'm just using 2 pieces of foam tape on the bottom. Now this is just a piece of acrylic that actually came with one of the robot kits that we had, but you could take any piece of mounting that you want to do and stick it on there. We like this because then you're able to, it's got the holes in it so that you can mount it. And it also is just something we had on hand. What you're going to be getting eventually looks like this. And while we have done it again using the acrylic here, and we're using pieces from the Make Block kit, but I have designed this so that it fits on this Pasco Dynamics cart here, which a lot of physics programs have. And so it fits right in there. There's 2 little alignment screws that hold it nice and tight in place. And it's just sitting on there, and it'll stay really nice and good. And then you can put it on your track. You can do conservation of momentum. You can do all kinds of things with it, with the sensors that we're going to have here on here. And then, of course, if you don't need it, then this just comes off, and these are free to be used for other labs or people who need them who aren't using the robots for it. So this is what it'll look like at the end of the day. Once you've got it in your case, and it's okay to go ahead and mount that. And then we'll put the breadboard on. And now you're going to find that not only is it a little bit harder to line up, but so you got to be really careful to make sure all your pins are actually going into the hole. But because of the case, it doesn't sit all the way down in there. And now it's still secure. It's snug. It's not a problem. Which the acrylic cases, the little laser cut acrylic cases, it was never snug, and so they would fall out all the time. So these do the job for us, but there are trade-offs. But overall, I think the trade-offs are worth it to have it in this kind of protection, this protected case right here, because that's going to keep it nice and rated. All right. So the first thing that we're going to build is the LED. Now there's a number of different systems that are all contained on here so that you can do a bunch of different labs, all with the same piece of equipment. With the original version of this lab, we had the students actually design every piece of it. And so they also, of course, had to do the software because I've got no way of predicting what their hardware is going to look like. We have since gone to a recitation and lab format. So the lab is now, instead of 2.5 hours, it's only 1.5 hours. And that just didn't leave enough time for the design. So we make each one of these robots then is identical so that the code is identical. And then I can just for each lab, I've got a pre-done set of code that the students can use to to gather the data and all that. But there's nothing stopping you from using this and then having the students expand on it if you want them to have more of a design experience. While the software here, I have the routines that I have written that access this, assuming that it is set up exactly the way that I have it right here. However, in the library, you can actually specify, well, okay, I don't want my LEDs to be on pins 8, 9, and 10. I want them to be on 10, 11, 13, or whatever. You can change that in there, and then the routine won't change as a result. So this allows the students to do actual Arduino programming as opposed to the block-based programming from MBlock without having to get too far into the weeds of making the Arduino work. And so you see here, there's just simple commands. My pads, you have to declare a pads object. That's what this is, so that you can access its functions, but you want to turn the red LED on, you just simply send that command and it will do it. All right. Also here we have, this is nothing more than in words, what we have for the design here. This particular breadboard, see if I can get where you can see that, it doesn't have the A through J and the numbers 1 through, 17 on here. It's not printed on the board like it is with the design. I did this design actually in Tinkercad. But you can still follow along by counting, how many holes down. But this is referencing the diagram right here. And you're going to see that in some of these cases, we've got wires that you would think, well, why didn't he just run a jumper straight across? And that's because this is the only way we're able to fit everything on this board. We use practically every row on this board for all of these things. But that's nice though, because it is an Uno footprint. And so that makes it small enough, yet still versatile enough. So, okay. So to start off with, then we've got our LEDs. Now, obviously the longer end of the LED is going to be my positive end. That's the end that we want to go into the pin that's referenced here. However, we want to make sure that this sits nice and tight on the board. So what we'll do is we'll measure this. So we want the green LED goes from A11 to pin 10. And A11 starts from 17. So 17, 16, 15, 14, 13, 12, 11, right there. And then that's going to go into Arduino pin 10. And as you can see, that's going to stick up quite a bit. And that's going to cause you some issues. So instead, what we do is we bend it like this. And then we trim off the leads. And you do have to be somewhat careful not to trim the leads too short, because you do need it to get all the way down into the breadboard, but you want it to lie flat on the board. So I've lost my pin here, so we will count that again. And so we want it on pin 11. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that pin right there is the one that we want. And as you can see, it looks like I need to trim off just a little bit more. I'm going to leave this here to mark my place. And that's a good technique, by the way, just to keep you from having to recount holes every single time. And really, you just trim it and you play with it until it's got a nice seat in there, just like that. Okay, the yellow LED works the same way. So again, do make sure that you are bending out the positive lead, since that's the one that's going to have to go into the Arduino digital pin. So we'll snip that off just for a starter. And then we skip 2 holes, so it's going to be A9, which is going to be and counting. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. Once you have all these, once you get a start on these, you'll have plenty of references, and you'll say, oh, well, it's 2 holes above whatever this particular one was. And obviously we want that to be in pin 10, or pin 9, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in there. That one's not going in nice and flat. So in this video, I may or may not edit out some of the fiddling with it. Sometimes I think it's worth seeing how it gets fiddled with, so that you can see what kinds of things you might run into there. So that's basically what we're going to look like. And then finally for the red, it's going to be on digital pin 8. And then we want to have it two holes down from that. Let's go ahead and trim that a little bit as a start. And the LEDs we have are so cheap that I actually had my students build these, and of course they messed up quite a few of them, and it was not a problem because you can buy these in bulk. And it just really, this whole system doesn't really cost a whole lot. There we go. Now the Arduino, of course, is putting out 5 volts. That's going to be too much current for these LEDs. So we need to throttle the current a little bit with a resistor. A 100 ohm resistor is plenty. So that's what we've got here. And so now we're just going to connect the leads for each one for each of the LEDs, so that we can have them all just use a single resistor for the entire circuit. So we want the resistor to be at G1. So this is 1, 2, 3, 4, 5. Oops, sorry. 1, 2, 3, 4. There we go. So we're going to trim that down. And that goes right there. So it has connection to ground. And the hole spacing is not quite enough. It's not quite wide enough to fit the whole resistor on here. So you have to kind of move it back and forth. As long as it gets all the way down to the bottom there, you're going to be fine. Now we're going to make this bottom row here be ground, because you're going to end up needing a lot more ground pins than you are 5 volts. The digital pins are going to generally be your source for your 5 volts. So you don't have that many things that are going to need to plug in here. These pins down here are 5 volts. These over here are ground. So what we'll do is we'll take one of these blue jumpers and we'll put it just like that. And now this entire bottom row of holes is going to be ground. And well, okay, first just that side, but then we'll put in the brown one here. Now that whole bottom row is going to be ground. And so anytime we need a ground, we're just going to connect up to that. All right, so the only other thing we need to do here then is to take our little blue jumpers. We're going to wire together all of our LEDs here. And let's see, so we need, let's see if I can see where this is. The LEDs, of course, are hiding where the pin actually is. And so you do have to make sure that you're going in the hole with the pin. Like so. And so you see that I have the negative lead from the green LED is connected to the negative lead of the yellow, which is then connected to the negative lead of the red. And then we'll use this orange jumper to connect to the resistor. And so that's our path. So whenever we turn on 5 volts to any one of these, then it's going to go down through the resistor and into ground, and then it'll light up. So the next thing to do would be to test the code. And there is a sample code included with the pads library. So if you install the pads library into Arduino, you go to examples, and you'll see one for each of the tests, each of the subsystems that we're installing here. So I've gone ahead and uploaded the LED test. You just go to examples and then pads LED test. And so when we plug that in, and you can see that all our LEDs are working just fine. Now, sometimes you have to wiggle these to make sure that you've got them well seated. This also allows you to check to make sure that you've got the connections that you think you have going into all of these, but this certainly seems to be working just fine. So the next thing we're going to do is we're going to build a light sensor, and here's the layout for that. But basically this light sensor here is nothing more than a photoresistor that we've got running through a voltage divider. So this is a 1 kilo ohm resistor here. You take 5 volts going into the into the photoresistor. It's the top part of the voltage divider. And then the 1K ohm resistor is connected to ground. And then we're reading off the voltage at the middle point right there at pin A2. So when you call this routine for a light sensor, it simply returns the voltage in volts from the light sensor. So it makes a nice, easy way for us to follow things around and detect light. And if they have two of them, then of course they can work like robot eyes and things like that. Now, with the photoresistor itself, you can wire it directly into the board the way we've done right here. The problem that you may run into there, though, is you've got to make sure that these bare wires here don't touch any bare wires that might be on the board. Otherwise, it's going to short out and cause you problems. We have a lab where we're doing diffraction, and so we need the diffraction pattern to go over the top of the robot. So we have a mast that comes up, and then the photoresistor is actually mounted on the mast. And so as the robot moves past the diffraction pattern, it picks up all the maxima from that. To do that, we plug this into some DuPont wires. Now, these particular ones, these short ones that we have here, it fits in fairly nice and snug. With the longer wires that we had, it wasn't so snug. It was coming out. So what we did was we just took some needle nose pliers and folded this over and squeezed it so that the wire ended up being a little bit thicker. Either way that you do that, then you want to take some heat shrink tubing, run it all the way up to the top on both sides, heat that up so that it shrinks around it nice and tight, and that's going to protect it really well. So for this one, we're just going to go ahead and wire it directly to the board since I don't have a mast handy here. And this goes in this top pin here, and then also in this row here. So 3 up from the bottom of the board on both sides, like so. All right, so now we need to give it 5 volts. And as I said, this row here is a 5 volt source. So we'll use a gray jumper to do that for us. And just move that out of the way. So now remember, this is not ground, this is 5 volts. So that's providing that 5 volts. This side is actually going to be ground. And then I need my resistor. So here's my 1K ohm resistor. And you see that I've bent it in such a way that it can fit, because it's got to fit in a space of just 3 holes, which is pretty tight, actually. And that fits right like that. And it can be helpful to use the needle nose pliers to push that in so that the wire doesn't bend. So tracing what we have here then, we start at 5 volts. That comes into the photoresistor, which then comes into so that's the top part of my voltage divider. And then the 1K is my bottom part of my voltage divider that goes into ground. So all we need to do then is to read off the voltage at that junction between the photoresistor and the 1K resistor. And so that goes here, and then we're going to read that into pin A2. Right, like that. And remember that the Arduino pins the analog pins are numbered A0, 1, 2, 3, 4, 5 from there. All right, so we'll load up the code, and I will switch over to the screen so that you can see on the oscilloscope how this is actually working. When we shine a light on here, you're going to see that it's going to get a greater voltage, because the way these photoresistors work is their resistance actually goes down whenever they're exposed to light. And so that'll give us a higher voltage whenever the resistor is exposed to light from there. Okay, as you can see, we're getting a reading here, and the voltage that you're getting here is pretty much just the ambient light in the room. I can make that go down by simply covering up the photoresistor here, and you see that drops very close to 0. When I point it at the light, let me make my camera view here just a little bit smaller so you can see what's going on there. So if we cover it up, it's going to drop. You can see what I'm doing here. When I open it up, then it's going to, as it gets exposed to light, that's going to start to go up. So we can change how much light it receives like this. And as you see, the response is quite good. It's quite smooth from there. Okay, for this next step, we're going to build an RC circuit, and here's the diagram for this. And this basically allows the Arduino through this pin right here, through pin 5, you can have it send 5 volts that'll start charging the capacitor that's up here. In the lab that we do, they test the difference between a 10 microfarad capacitor and a 100 microfarad capacitor, different time constants for each one. They can simply pull that in and out and change it as they need to. One thing I did do, though, with my board was I colored in, because I'm using electrolytic capacitors, I colored a big black dot on the top connector up here and a big red dot on the bottom, just physically on the breadboard, so that when the students pull the capacitor out, they know which way to put the next one in for that. And you may find that that's kind of useful to you. We've got a 100 kilo ohm resistor here for the resistor part of the RC circuit. The rest of it is pretty straightforward. And while, again, like I said before, it might look a little convoluted because I have to fit all the rest of the components in here. But you see that we go from pin A5, which is going to provide that 5-volt source. Then it comes up into the resistor, then through the capacitor, then comes back down through here to ground. And so remember that this bottom row right here is ground from that. And so that's your circuit, but then we want to measure the voltage across the capacitor. So we pull that out in between the capacitor and the resistor. That comes down through here, and then the voltage is being read at analog pin A1. So a couple of options you can do. Calling the RC circuit function then just simply returns the voltage, and it is in volts of the current voltage of the capacitor. Charge RC just brings that pin 5 to 5 volts, and it'll stay there as long as you decide you want it to there. Drain RC then will turn that off, and it'll turn it to 0 volts. Pulse RC allows you to be a little bit more automated. In our lab, we had them actually control the time because they didn't know necessarily what their time constant was going to be. But here you can specify a time constant that you want for how long you want it to charge, how long you want it to discharge, and it'll do that automatically so that the students don't have to work out what those times have to be. All right, so let's start with the assembly here. Okay, we will start from pin 5 down here, and that then needs to go up to B6. So 1, 2, 3, 4, 5, 6. So that's going to be right there over to pin 5, which is going to be right there. And again, you may find this easier to manipulate if you're holding this with needle nose pliers instead of trying to use your fingers with it. I tell my students I've got fat fingers. Okay, so it's one dot, one space below the red LED pin. That's where that one's going to go. Then we're going to need a yellow that is going to take me all the way up to B13. And that's going to be connected to our pulse pin, as we call it. And that's going to be B13 right there. So 4 holes down, and then we plug it in. Then we need our resistor, and of course we're going to need to trim that. So here's our 100k ohm resistor. Like so. Just like that. You gotta be careful about cutting these resistors too short. There's a strong temptation to do that, and then you'll find that you don't get a good connection. So if something's not connected, that's probably one of the first places you want to look. Okay, then as I said, I have an electrolytic capacitor. So the stripe on here is the negative side. So that would need to go up here. But again, you probably don't want this sticking up like that. So make sure that you trim that. And we'll trim it. We'll start off maybe about like that. And if you trim it too short, well, that happens. And it's not a huge tragedy. One thing you do want to make sure, though, is that your leads aren't twisted, because that could be embarrassing. There we go. And then that fits down right on like that. Okay, so now we need to make the path back to, so we've got the path from power up through the resistor, through the capacitor, and now we need a path back down to ground. And so we do that with a couple of these brown ones. Like so. And then the blue one to bring us down even further. And I tend to run the blue so it goes right in between these two jumper wires for the LED. And that's got to go with 4 holes. And then and there you go. So that's going to be tucked in nice and tight, just like that. Okay. Now the last step then to bring it onto ground, we need a gray. And that's just going to connect the blue, and that goes actually right underneath the yellow. Get my photoresistor out of the way. Right like that. There we go. So now we've got our complete path. So we start here at Arduino pin A5 or D5. Then it comes up through the resistor, through the capacitor. From the negative lead of the capacitor, then it comes down here, connects up to the blue, comes down through the blue, connects to the gray, and then goes to ground. So the other thing left that we need to do is to be able to read it, because we would like to actually get data out of that. So we're going to do that on the other side, since we're going to be reading that on the analog side. So this pin is connected at the junction between the resistor and the capacitor. That's going to allow us to read that voltage there. And then we'll take our green and we'll come all the way down to here. And it would be helpful to count how many holes up that is. So that's going to be 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it looks like it needs to be 1 higher up there. And if you find you've got these in the wrong place when you start adding more things in, it's pretty easy to move things around. So let's double check here. 1, 2, 3, 4, 5, 6, 7, 8. And that does say, in fact, it should go to I8. And then, except I do want it one pin over so that I can have my yellow jumper that's going to read it at pin A1. And I've tried to lay these out so that the pins are being accessed in as neatly a way as possible so that students can actually follow along with what's going on here. All right. And that's basically that. So the only thing we need to do now is to load the code. And again, these are found in the examples section of the library. And then what you're going to see is we're going to charge this capacitor and then we're going to discharge it. And you'll see the typical RC curve coming from that. So as you can see, we've got the circuit running here. And this is the charge cycle. So it basically is applying 5 volts to the charge pin A5 or D5 here. Then it turns it off, sets it to 0, and the capacitor charges. And that is obviously a typical RC circuit graph. They can extend that time by using the pulse RC, or they can just write their own code that's going to determine how long they want to let that go. The lab that I have, it has some user definable variables at the beginning where they set what they want the charge and the discharge time to be, and then the code itself takes care of all the details from that. And that's really all there is to that. And so this allows them to actually experimentally determine the value of this capacitor here by measuring the time constant, and then of course they measure the resistor with the multimeter, and then from that they're able to figure out what the experimental capacitance of that capacitor is. The next experiment we're going to do is going to be an induction coil. And so the way this works, I've just made these by wrapping magnet wire around a paper towel roll, basically. So this is 300 turns of magnet wire. We do 300 turns and 100 turns as well. And then I soldered the end of the magnet wire to a DuPont cable, and then used just heat shrink tubing to hold that in place nice and secure from that. And then these two ends here will end up plugging into the main board. The black end, it doesn't actually matter, but I've got it coded so I've got it set up so the black end they'll know to always put into ground, and then the red end is what they're going to be reading off of. Also, when I do this, I put a little red dot on the board where this one should plug in so that they can find it whenever they're swapping out coils. Because they're going to have to swap between the 100 and the 300 turn coil. Having those places marked, and I just used a Sharpie to mark where it was, that you'll find is going to be very helpful when you're doing this in class. Okay, so let's go ahead and start the assembly here then. So we'll start over here on the power side. Now I am reusing this wire right here. This is the wire that's actually from the voltage sensor, or from the light sensor part here. So that's not a new wire. That's one that's already there. And so then we will take the blue then and come up between there. Now here again, we're starting to tuck wires in to all these different places. So sometimes you'll have to just move the existing jumper wire over so that you can get it in there, because we really do use almost every single row on this breadboard. And then the last one goes, so there are 5 holes and down, and that's going to be here. So just making sure we're counting here. That's 1, 2, 3. Let's see, 1, 2, 3, 4, 5. So that's going to be right underneath that resistor. Like that. And then we took it in so everything's nice and flat. And let's double check. 1, 2, 3, 4, 5. Looks good. All right. Next, we need to be able to connect that so that we can come around the loop over to the other side. And so we'll take another brown wire here. And this, you may need, we're going to temporarily unplug the green LED so that I can get in here, because this wire actually rests underneath the green LED. And it's going to connect just prior to the connection for the for the capacitor. So in this third row of holes here. So it's going to tuck in nice and neat there. And then we'll take this and we're going to put it back so we don't forget where it goes. Like that. Anytime you start moving these around, there's a good chance that you've made it so it doesn't make a good connection. You may want to rerun some of the LED tests or whatever just to make sure that everything's still working the way you expect it to once you've got everything fully assembled. All right, so now we need to go across then. And now we're doing the third row. So this is going to go right underneath this one that we already have going across for the other sensor, just like that. Now we've got 3 resistors, and what this is another voltage divider. But the way this voltage divider is going to be set up is that it will take the readings from 0 to 1023, the analog ADC units, and it will convert that to a voltage between -6 and +6. And so there's no other real way to get negative voltages that the Arduino can read. So this will automatically scale it so that if it's right in the middle at 512, that's actually going to be 0 volts. And then 0 ADC is going to be -6, 123 is going to be +6. And the code takes care of that automatically for you. The library takes care of that automatically for you. So what you're reading at the analog pin 3 here is the actual voltage, be that from negative to positive. And so this not only serves as a way to to measure the voltage from the coil, but it's just a general voltmeter. And so the way I have my students test it is by just taking 2 DuPont wires, and connecting it up to a AA battery. They should get roughly 1.5 volts when it's connected properly. And then when they reverse the polarity on it, they should see that they get negative 1.5 volts. And it comes out quite well for that. So at the top of the voltage divider, then we're going to have our 1K resistor, which we will then trim. Like so. And that's got to go down 1, 2, 3, 4, 5, 6, 7 holes. So let's make sure that we're counting that correctly. Leave this up where you can see 1, 2, 3, 4, 5, 6, 7 holes right there. All right. Next, we need our 4.7K resistor, which is this kind of fat one that we have right here. Or I'm sorry, that's the yellow one, is the 4.7K. And you should test these with multimeter before you get in there. I just happen to have the existing one already set up for me so that I can refer to it. And this goes in the same hole as this initial one. And then we need to come down from that 1, 2, 3, 4. So 1, 2, do the bottom of the pin here. So 1, 2, 3, 4. And then connect up, right like that. Okay. And then finally, this is going to be our 1.2K ohm resistor. This one's so big because I happen to have some half-watt resistors instead of the quarter-watt resistors that I'm using for everything else. There's nothing really special about these, but they're big just because it's a half-watt resistor. And there's no need for that because the power draw on this is actually fairly small. And so we will connect that then at the junction point there. And then it needs to come down 1, 2, 3, 4. After that, it's going to be the 5th pin below. Let's get myself something to count here with. 1, 2, 3, 4, 5, 5th pin. So we're looking good. All right, like that. Okay, so now we need our connection to ground, and then the connection that we're actually going to read out. So we'll take our blue jumper, and this is going to go down to our A3 reading, which is going to be down at the bottom. And then as you can see, I'm just tucking it in between our existing components, trying to get everything to lie as flat as we can possibly get it. Because right here, we're going to need to come from the bottom of this pin, the bottom of the 4.7 kilo ohm resistor, comes down there because that is going to have to get connected to ground. And so that's what we're going to do right here. And I'm going to temporarily take out my photoresistor so that I can put this in. Right like that. And now put that photoresistor back in so that I don't forget where it goes. There we go. And so the last bit that we need is to be able to read it off. And so we're going to need our gray wire, which seems to have flown the coop. It's okay, I've got more. And our gray wire is going to go from pin A3 up to where that blue pin, that blue jumper comes down. Like so. So we actually use all of the analog pins except for A0. Now with an Arduino Uno, pins A4 and A5, those are your SDA and SCL pins. So for example, we'll use those with the accelerometer. So they can't be used for anything else. Most of the rest of this stuff you can actually switch around to whatever you want. And as I said, right now I've still got A0 available if that's something that we decide we want to do. But tracing the circuit then, we've got our connection here to power. Let me get something that I can point with. So it starts here, connects up to power, goes up the blue wire from here, goes to the brown wire to here, goes across, comes down the resistor. I've got 3 things plugged in for the resistor. I've got 2 other resistors and this blue wire. The blue wire comes down, and that's where we're actually reading it off. So we're just reading off the voltage at that junction right there. And then for the brown, for the 4.7K, it's connected to this blue, which is then in turn connected to ground. So the only thing that's not connected to anything is the bottom of the 1.2K ohm resistor right there. And so that is where you're going to connect your coil. So we take our coil and we plug that in right there. And then the other end needs to go to ground. So we'll just put that right like that. Now, when you test it, if you take a bar magnet, as you're going to see here, and you run it in and out of the coil, you're going to see that you're going to generate a voltage from that. And when we do the experiment, we actually have them drop it through. So we've got a double-sided or a doubled-up yoga mat here to cushion it. And it'll drop through, and you'll actually get the positive and negative peaks when it comes through. So let's load up the test code, and let's see that we're getting what we expect. Okay, so the way the code has it is that it's multiplying the voltage that's produced by a factor of 100. The voltage itself, no, but the reading of it so that you can actually see it. So the students always have to remember that they're going to have to divide out that scaling factor. That's why the noise here is actually fairly high. It looks high, but it's really not that bad because we multiply it by 100. Notice that I do have them hold the coil by the cardboard and not by the magnet wire, because you're going to find that your body actually interferes with that quite a bit from here. So let's let that settle out for just a minute, and then we're going to drop a magnet through it, and we're going to see that we get some good results. All right, so we've got the magnet here, and you see that when the magnet goes in, we get a nice result. If I take it and I drop it, then you see we get the positive and the negative peaks as we would expect. All right, next up is the ultrasonic distance sensor. Here's the layout for that one. This one's actually very easy because it doesn't require any external parts on the breadboard itself, so it just needs to connect up. It is important that you notice that we have, the library assumes that the trigger pin of this 4-pin ultrasonic sensor is connected to pin 6, and the echo pin is connected to pin 7. The library can also handle a 3-pin sensor here. It will automatically just go ahead and send on that one middle pin, and then switch it over to be receiving when that comes back. And it'll take care of that automatically. Because these are actually generally quite easy to find on eBay, the 4 pins, and they're maybe a little bit more precise than the 3-pin version. The library is set up for default to use this, but you can easily modify that to use a 3-pin if you need to. All right, so connecting these is very easy. We've got these DuPont sensors here, or these DuPont wires here. And the way we mount this is we're going to mount this on the front like this using foam tape. So and it's printed on the card what it is, so it's actually very easy. So we plug in the ground here. And then next is going to be echo, which I am using a white wire for. And then trigger, which I'm using green. And then finally VCC, or 5 volts, that we're going to use red. And then you just plug it straight into the board. You can twist these if you want, but you don't actually have that far that you need to go with it, so it's kind of not worth doing in that particular point. The wires are not long enough really that they really get in the way from that, and you want to make sure that you're getting a good connection here. So we take the red one, goes directly into 5 volts here. The white is our echo pin, so that's got to go into pin 7, which is the far one here. Green is trigger, that's got to go into pin 6, which is, we may have to scoot the pin 5 wire out of the way just a little bit to make sure that goes in all the way. And then finally, this goes to ground. And I'm using the bottom row ground rather than connecting it here because it's a lot closer. And then that just comes in like this. We have foam tape. We use 2 squares of foam tape. And I got this at Ace Hardware. You can buy them in fairly large packets and they're not expensive at all. There may be better ways to secure this, but this was certainly the cheapest and the fastest. So we will stick that on, peel the backing off. So what I do is we're gonna connect it this way. So I actually connect it just below the pin connections here. That way it's all reasonably the same height. And if you decided that you wanted another one on there, you could, but then it can sit on top of the acrylic that we have here. And that keeps it going, that keeps it from pointing down too far and makes everything work out really well. So that's all you need for the distance sensor. To read the value, to read the distance in centimeters, they just call the distance function and it will do a ping and it will tell them the distance in centimeters, and it automatically converts the time delay for them for centimeters. Okay, so we got the distance sensor connected. My camera, a little bit hard to see, but here it is right here. And as you can see, there's going to be some noise because as it works simply by ultrasonics. But if we use this other case as a barrier, then you can see that we can move it in and out. And well, at that point, I got a big spike because I got a big distance. This is limited to going to 400 centimeters. So that's going to be the farthest distance. And then the closest distance is going to be about 2 centimeters that it can go from. And so you can do these kind of graphs. We've got a large barrier. And of course, that sits on top of this. And so as it slides, then it's able to get fairly accurate readings, and they can plot the position versus time, figure out the voltage, find the slope of the curve, or figure out the velocity, take the slope of the curve of the velocity versus time curve then, and then they can get the acceleration. So you can see we can point in all different directions, and it's going to read that distance quite well. Okay, so the last piece of real sensor that we have to work with here is the accelerometer, which is both an accelerometer and a gyro. And the connections to it are very straightforward. We do need to use the SCL and SDA connections on the Arduino, so that's going to commit us to using A5 and A6. The robot, when you ping the accelerometer, you get in each axis, it's already does the conversion for you to meters per second squared. So if you want G's, then obviously just divide by 9.81. It'll also return the current gyro position for that. You do have to be sure and call this init Excel gyro, because the program will actually suspend until it gets a non-zero value for that. This causes some consternation with the students. If something has come loose, particularly with this small little chip that you see here, if something has come loose so that it's not getting a good signal from this, it actually will stop the program and just simply sit there and wait. And so the students are going, nothing's happening, nothing's happening. There is a very good chance that something's up with your accelerometer. They are a little bit more problematic than I particularly like. This is an MPU 6050, as you can see here. But overall, they do the job, and they will work. But if you need to, in general, if you're not using it, it's a good idea to go ahead and disable it. It's a good idea to go ahead and disable it, because it's got to poll roughly 100 times a second to get a good average for the values for the acceleration on there. And so that requires a whole lot of processing power, and also creates a whole lot of noise, so that if you are trying to do something, for example, with these induction coils, the noise actually gets overwhelming. So in general, go ahead and disable it. Leave it disabled unless you're doing something that actually needs the accelerometer, kinematics lab or something like that. So connecting these things up are pretty easy. This particular one came pre-soldered. Most of them don't. I'm wishing I hadn't gotten them pre-soldered, but what I did was I just cut off the four pins over here, the XDA, XCL, 80, it looks like ADO, and the INT. You're not going to use those at all. So the nice thing about that then is the SCA and the SDA and SCL pins are actually where they need to be to simply plug it into the board just like that. So all we need to do is to give it power. So the inner one is ground. So I'm just taking one of these DuPont cables here. I'll plug that right there, and I'll take my red one to be my power. I'll plug that right there. And then we just connect them straight in. And I'm using, we'll put that out of the way for now. So I'm using my ground connection here and my 5-volt power connection here. That then bends around so that that plugs in. And getting a good tight fit can be an issue. You basically need the DuPont, the end of the DuPont cable here, to scoot over just a little bit so that it snaps into place. I don't know if you can see that right there, but you need to have that scoot over just a little bit so that that gets seated all the way down. Otherwise, you've got no chance of getting it to work. All right. And that's really all there is to it. And that's a nice convenient mounting place for it. So you're not getting a whole lot of jiggle in it. The only jiggle that you're getting is from the robot itself, which is what we want with that. You do have to be really careful to make sure that this thing stays plugged in. It will kind of try to work its way out. If you want to make it permanent, a little bit of hot glue will do wonders for it. We tend to not keep these running, and so I have not hot glued mine, but I do caution my students all the time, make sure that your accelerometer is making good connection. And if the program isn't responding, it's probably waiting for the accelerometer. So let's test it up and let's see what we get out of it. Okay, so we've got it running here, and you can just barely see on the video that we do have a power light on there. Just because you have a power light does not mean necessarily that everything is running as it should be. It just means the board has power. Oftentimes, it's not the power that's the problem. It's the fact that it's not seated in that pin A4 and A5. You can actually run 2 extra DuPont cables and mount this pretty much anywhere you want. This was just seemed to be a nice convenient place for us. The code is running, and as you can see, I've got this running. This is time, the X acceleration, the Y acceleration, and the Z acceleration. And so you can see that it's measuring the acceleration due to gravity even when it's just sitting here. And that's kind of a neat little discussion that you can have if we set this running again. So we get some data while it's sitting still. You see that we're getting almost zeros for my X and Y values, and then around 9.8. There's a lot of noise that's going to be in this, but just because of the way that the system is set up. But overall, you can certainly see, like for example, we do impulse with collisions and things like that, and the accelerometer is more than capable of picking that up. Again, though, it is noisy. It is a power hog. You can't run the accelerometer if you are running motors, because if you're trying to run motors directly off of the board here, even with a motor driver, sometimes you'll have problems with it actually being able to get all the power that it needs, and the board will brown out. So a little bit problematic, but since a lot of what we do is with forces and therefore with the acceleration, it actually is a really critical piece of hardware. All right, so the last piece of equipment we're going to assemble here is going to be the Bluetooth. Now, you don't actually need the Bluetooth. In most cases, you've got plenty of serial cable. Even when you're doing dynamics experiments, most of the time your serial cable, your USB cable is going to be long enough that you can just run it. And that's the most trouble-free way to do most of the physics experiments that you're going to do. Certainly if you're doing electrodynamics or something like that, there's absolutely no reason to use Bluetooth for it. Bluetooth has a lot of problems. The mate block has a Bluetooth adapter that connects to a little Bluetooth dongle. And that way, rather than connecting to the computer, it connects to the dongle, and then you can use that with each one. The problem with the Bluetooth adapters like you see here, which these are actually quite inexpensive and very easy to do, is they're going to pair with a specific computer, which now means that pads is connected to a specific computer. If you've got more robots than you have computers, that's going to be an issue, and you're going to have a big problem with that. The connections are sometimes a little wonky if you've got a lot of Bluetooth going around, a lot of Bluetooth devices running in your classroom, which of course, if you've got 12 or 15 of these running at once, then you certainly will. So my advice is use the USB cable anytime you can. If you're in a situation where you have to have the Bluetooth, so for example, if you've got a free running rover that's doing a pathfinding mission or something on the ground, well, then you don't have a choice. If you want to send data, you're going to have to use the Bluetooth. And if you do that, I recommend only having one or two running at once. That'll help kind of limit some of the interference. But unfortunately, with this particular adapter, there's no way around the fact that it's going to be paired to a specific physical computer. And you really probably don't want it paired to more than one, because both of those computers may be running at the same time, and that's going to cause you a lot of issues that you just don't have time to solve when it comes to the lab. Mate block system is somewhat better, but it's also quite a bit more expensive. These are actually extremely cheap. So the only disadvantage to using these is that, as you can see on the back, while it will work, let's see if I can get it to where you can read that. You can kind of read that, but while the power will run 5 volts easily, the logic level on it is only 3.3. So that means when the main board is communicating with this, which is pretty much what you're going to do all the time, you can't run the 5 volt logic through this that you would normally do from an Arduino board. If you've got something like a Nano that's running 3.3, that's fine. But you're going to have to use a voltage divider to step this down from 5 volts down to something below 3.3. So when you're transmitting to the robot, well, there's no problem at all. You can connect that one directly. You don't have to have a voltage divider for that. So what we're going to show you is how to set up that voltage divider then, so that you can run this safely. Okay. All right. So first things first, we're going to use a 1 kilo ohm resistor and a 2 kilo ohm resistor. That'll step it down plenty for us. So we'll do our 1K first. And I have that running between ground. The 1K is going between B1 and B4. And as you can see, things are getting quite crowded in here. So it starts to get to the point where you have to take stuff out to put other stuff in and then put it back. I'm going to disconnect my ultrasonic here for just a second. So from B1 to B4, just like that. Okay, so that's connected to ground. And then my 2K resistor, the only way we could fit it in was to run it at an angle. So that's what we're going to do here. So we'll trim that. And so that goes from D4 to E2. So this is E2 right here. And then this is D4 at the same level. Remember, it's a voltage divider. So in the same row of holes as the 1K. And it's not going to fit exceptionally well because it is at a diagonal. So this is a case where I may need to go get my needle nose pliers to get that to set in very well. All right, just like that. And then we will use this brown jumper here to connect. And the way I've got software serial set up for the board is I've got it running out of pins 2 and pins 4. All right. So digital pin 4 then needs to connect to the top of this voltage divider, which is the 2K resistor right there. Okay, so then be very careful about that. It needs to connect, get something I can point with. It needs to connect from pin 4 right here. This is, oops, that's pin 3. Let's make that pin 4. Remember that they're labeled 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4. So it's going to be the one right under pin 5, the original LED or RC circuit that we had. And then it's going to go in the second row of holes. There we go. Because that has to connect up to this resistor right here. And then that row, the middle row from that, that's what's going to connect to our receive pin on the Bluetooth. So looking over here, the receive pin, we're using a white for it. And we will connect that to the top right there. And then the green one, the transmit pin, we can connect directly. To our Arduino pin A2. And if your robot is not going to receive commands, you don't actually need that one at all. So that's something to keep in mind. You can decrease some of your pin work here, some of your cabling, if you don't need that one. And then we have ground, which of course is going to go to ground. And we will plug that in right there on the end. Theoretically, I have another hole in there, but that's okay. And then finally VCC. Which then has to go into voltage, like so. All right, I'm going to go ahead and reconnect everything that I pulled out. Oh, actually, this is going to have to go into my bank of ground because all of those holes are being used. There we go. And then we'll put our photoresistor back in, just to get everything back up and running. So you see things start to get a little bit tight with the connections here. One, two, three. I need to have that right there. Okay, we'll finalize that later. But that's how it's going to get connected. And then you can use foam tape if you decide that you want to use this. You can foam tape it onto the side. A little bit longer cables, and you could actually put it horizontally here like that, which is probably one of the best ways to do that. And then it's just a matter of pairing it up to your computer and sending data over it. So, as I said, this is not necessarily ideal, but as you can see, we've got the work. And the blinking light here means that it's looking for a pair with that. And so you would pair this just exactly as you would any kind of Bluetooth device. So you go into Windows, go into add a device, add a Bluetooth device. The pairing code for it is simply 1, 2, 3, 4. Once you do that, it will connect, or it'll be paired, but it won't actually connect until you connect it to the serial monitor. And so you'll find that what happens is you'll have 2 COM ports when you connect this. One of the COM ports is actually not going to be used, and usually that's the second one. You'd want to verify that. But then the first one that's listed, so for example, it may say COM 7 and 8. You would probably use COM 7 then. That is the one that you're going to connect your serial monitor to. Then when you use software serial, then all the data will go out to that. Now, the way the code is set up, if you have used Bluetooth, if you run this command here, then it will automatically switch the variables so that it will send all of the data, the send data and the plot data, which are these functions here, will go out over Bluetooth. Missing an E there, but or you can send this command, which is the default, the use USB, and what that will do then is it will send it over the USB cable by default. This sets the baud rate. I suggest using 9600 for everything. Your Bluetooth has to be 9600 unless you get into changing that in the parameters for the Bluetooth itself, which is kind of beyond the scope of this video here. There's plenty of videos on YouTube that'll show you how to do that. Other things here, this is our data sending routine, which I've put here. So set the number of decimals. That tells you how many decimals after you want to send. So it's not significant digits. It actually is the number of decimal places that are shown there. Then we've got some custom ones already set up. If they want to send XY data, so there is a function built into the library called time. So it's mypads.time with a capital T. And so you could send time, comma, whatever your data is, and then it'll automatically send it out in XY format, which is kind of handy. If you've got 3-dimensional or 4-dimensional variables, then you can do that with, these are already done, or you can make your own. Send data just by itself will send a single number, but won't send a line feed. So then you could send a text string that was just a comma, and then another send data that was just a number. All that would be on the same line. Then when you're ready to do a carriage return or whatever, then you would send the line feed there. Plot data works the same way, except it only accepts one variable. Now, this is functionally identical to send data here if I added a line feed to it. But what we have that set up for, since the serial plotter only uses one row of numbers, it will only take one number, and then it plots it against its own kind of internal time steps with that. Then the students then can, if they want to look on the oscilloscope, if they want to look on the serial plotter, they can uncomment plot data. And then when they're ready to actually take their data, they comment the plot data and uncomment the send data for that, so that it saves their time and their position or whatever it is that they happen to be reading. So that function works out fairly well. All of these functions, again, work both with the USB cable and with the Bluetooth. And you don't have to do anything different in the code. All you need to do is specify with this command, use BT or use USB. So there you have it. We've built it from scratch. This battery pack you can get off of eBay. We're actually using the ones that came with the original Make Block robots, but they're basically the same. 6 AA batteries will provide the 9 volts that it expects here. And you see that I've run the cabling, just kind of tucked it under. And again, we're using the acrylic here with just foam tape holding it in place. These little blue pieces here and the connector here, those came from the original Make Block Ultimate 2.0 kit that we used originally. We're not actually using the Make Block equipment anymore, just because we found that it was cheaper to use the standard Arduinos when inevitably things break. And we decided that we really wanted them all to be the same. So since we couldn't afford the $200, $300 for another Make Block kit, whenever one of those broke, we can pick up one of these things for $7. Well, that was kind of hard to argue with that. So these we use for sensor mounting. Like I said, I have a mast that comes up for when they're looking at the diffraction pattern. They're measuring the diffraction pattern with this photoresistor here, but it needs to be up higher so that the pattern can go over the top of the robot. You can mount all other kinds of things. The other thing that we wanted, though, was to make sure that we could interface with the Pasco dynamic cart and still make full use of that. These particular ones also have this particular one also has the plunger on it, which will still work. So you can still fire that as you need to with the button right there. Get that back on. But so you don't actually have to use this acrylic system. There's plenty of room to simply Velcro your pieces right onto that. And then you can use it however you want. We also have some blocks, some wooden blocks that slide down an inclined plane. They already have Velcro on them. And so we can Velcro this to that if we wanted to. We had the parts, and so we just decided to make it easy so that we could swap these out for the instructors that are using the dynamics cards but aren't using the pads. And this makes it so that we can all kind of work together happily with that. But however you decide to do it, if you decided that you wanted to have autonomous robots, so for example, the first semester that we did this, the robots were actually solving mazes and things like that. This also works well. You just have you simply have the students build just a little chassis to hold the motors, and then at that point you would want to probably take out this board and replace it with a motor driver. The only things most of the time you're going to need in a dynamics lab like that is you're going to need this. You're going to need the ultrasonic sensor. You're going to need the accelerometer, and which I don't have showing in this one because we've taken it off, but here it is on the other one. And you're probably going to want Bluetooth with it if it's free roaming, if you're going to be collecting data. We also have line followers. You can in the library, you can specify that you want to use servo 1, for example, and that will replace the red LED with the servo, so that you can use the servo code to control that. But then of course you have to remove the LED because we're out of analog and digital pins here that we can use. Same thing. So you can do up to 3 servos by just using the library to indicate that you want to replace those LEDs with that. You can also use the line follower by replacing your RC circuit and your light sensor with that. So that can plug into the analog ports for that. So very flexible system and very reliable, does what we need. The students enjoy playing around with it. The general labs that we do are all focused on gathering data and just more like your traditional physics labs. Our engineering labs, though, are more about design to accomplish the same goal. So if you've got any questions, please don't hesitate to contact me, and I would be happy to answer them as we can.